Welcome to part 2 of my discussion of my approach to the Collatz conjecture. This covers what I went over at the end of the previous part back in Minecraft, and you'll recognize roughly that these are the same equations from the sines, and I've split them up into 4 different components as I did on the sines, and then at the end I tacked on a row of the actual product. Now I haven't populated this green column with any numbers yet because I want you to see what this does. Ultimately, if you encounter a negative number with the mod function, it says, okay, we're way past done, so let's wrap around. And if you take a number, say 0, and you apply it to a negative value, so 0 minus 2 becomes negative 2, and then you mod 6 it, mod 6 says, whoa, 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 we're already negative here, let's throw some positive at it, so let's add 6. So negative 2 mod 6 becomes 4. The remainder is 4 because mod just hates negative numbers. And then you divide by 2 as per the rules for this part of the function, and you get a 2 for all these. So all these are zeros. It assumes that this blank space is a 0 instead of treating with divide by 0 nonsense. Now, moving over to this, there's nothing to enter, and there's no negative numbers, so the modulo says, okay, we're done. So mod 0, 0 divided by 3 is 0. This goes, okay, we have a 0. We're going mod 2. All right, so far so good. That gives us a 0 still. And now we're subtracting 1 from it. Okay, this is possibly problematic. All right, now let's apply the absolute value. Okay, now we're back in the positive range. We have a 1. And then this just simply multiplies by 1 less than whatever the input number is, and this will come into play for the whole equation. I just wanted you to see what all these different steps do by default. Now, you can see I've already colored these into this. I was going to do red, but red just really stood out way too much. So I have this, I don't know, like some sort of salmon-y color. And then we have a blue that isn't so blue that you can't see the text in it. And I even bolded the numbers just to be sure. Now this spits out a negative 0, and, well, the reason is because it's got some negative number here that it's multiplying. So we have 2 times 1 times 0, and then it says times negative 1. Well, negative 1 times 0 should just be 0, but because of the spreadsheet, it slaps on a negative in front of the 0. This is just an artifact of programming. It doesn't actually affect the outcome. This only happens at 0. Now, let's fill in a number and see what happens. So we've added the 1, and what we find out is it still doesn't like the negative value, so instead of wrapping around by 2 or by 4, it wraps around by 5 because this is going to give it one extra boost. We have 1 minus 2 is negative 1 instead of negative 2. The mod 6 still says, whoa, 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 let's throw some positive values at this, and it gives a 5, and 5 divided by 2 is 2.5. Same thing that happens for all the other steps happens here. We just end up with a 1 in this case, and divided by 3 we get 1/3, and that's what 0.33 is. This guy says he's an odd number. 1 is an odd number. So let's give that a 0, and just as an artifact of it being a 1, it also multiplies by 0 here, and that just happens. And that's, I think it's the rule of small numbers. It basically says when you're close to 1, or when you are close to the beginning of a sequence, things aren't really interesting. It's not until you get farther out into the field that things actually start to make sense. So this 0 is just an artifact of getting started. We'll call this the seed. Now, let's go ahead and add some more values to this. We'll go with a 2 here and see what that populates as. 2 minus 2 is 0. Mod 6 is a 0 divided by 2, yada yada, all these. And we end up with a 0 as the output here. And the reason for this is because this one was a 0. Now, this removes the values to less than a what I call a split point, and that means that this right here would be a split point, and this is row number 5, but it's going to be number 4. Let's go ahead and fill these next two in, and then I'll just do the rest by formula, or maybe with a cut or whatever. But we have a 4. Now 4 would be a split point, but remember what I said about avoiding the trivial loop of 421, 421? Well, this is the same thing here. We want to avoid this 4 becoming a 1, so we don't care about this split point. We are just saying, alright, I acknowledge you exist. Let's move on with things. So, let's move on and see what these two other blues are going to be. And we have a nice progression of zeros, and then 1, and 3, and 5, and this will continue as you add all the rest of the numbers, 7, 9, 11, 13, so on and so forth. It will spit out all the odd numbers. This is wonderful. This is exactly what was needed. It will only provide a whole number non-zero answer if none of these individual terms are 0. And as you can see, none of these are. Here's the 10 that I mentioned before, the mod 1 on it, and then on this step we divide by 3, and on this step we determine that it is an even number, so we multiply by 1. So this is, when this is a 1, it says, alright, this is what we want. This is number 1. And then this one says, alright, this is even, this is what we want. Multiply by 1, you can do this. Now, remember, we're looking for n minus 1 divided by 3. Well, that's what this is. This is the n minus 1. And then finally, this is it divided by 3. We've done it. N minus 1 divided by 3. Hidden in all of this nonsense that is basically a program written into the form of a formula, and it spits out either zeros or odd numbers. It's wonderful. But enough about that. Let's move on to what I did with this. On to this tab called All Odd Formulae. Now, this does not look anything like that graph that I showed you in Minecraft. This is, well, up to step 16, all of the numbers in the Collatz sequence. All of them. Now, 1 is the seed. We know this to be true. 2 is step 1, and this means that it takes 1 step to get from 2 to 1. We have a 16 here, and that splits to become, if you remember from over here, the 16 was one of the numbers that gave us a value, so we have the 5. So 16 becomes a 5. And also, because all numbers get doubled no matter what, 16 becomes a 32. None of these are solutions or have solutions with my formula that we covered, my monstrosity. So both of them just simply get treated to multiplication by 2, and then those two generate odd numbers. So this process just continues and continues and continues on into the vast fields of infinity. Now you can see that this turns into sort of like a trumpet or a funnel or whatever, and you'll find overall that it grows by about 26% per step. There are 26% more new odd numbers per step than there were total numbers in the previous step. So let's say in step W we had 100 numbers. Then in step W plus 1 we have 126 numbers. That's an approximation. It's not always going to be exact. There's some decimals going on out there, and there's a little bit of rounding. When I say 26, it's about 26. But now that we have a picture of all of the numbers, we can actually start doing some fun stuff with this. So I've come up with a base formula to determine what happens with all the numbers as they trend. Now, once a number becomes a point on this chart, yes, it could become an odd value, but for sure it will always also become double whatever it is. A 35 here will become a 70. And we are glad that this happens because we can do math with this. We can actually do some interesting things. Because this 70, though it may also produce a new value, which it does, the 70 becomes a 23, it also doubles to become a 140. And these aren't perfectly lined up because there are numbers being wedged in here. I can't really line it up as it is right now. And that's just an artifact of how I have this laid out. If I made these numbers really big by proportion, if I made the 1 way over here and this whole field be a 1, then yeah, I could get things to kind of line up, but I'm not going to do that. So we have some results here, and we have enough results that we can test for some predictions. For every new value that is produced, you can create a formula that will follow the chain of even numbers that come from it. So if you start with this 1 over here, everything that follows after it, 2, 4, 8, 16, 32, 64, on and on and on and on, will follow this same pattern set up by this position right here. You find an odd number, or you discover an odd number, say, I discovered a 1 over here. You multiply that by 2 and raise the 2 to the power of whatever number you are, whatever step number you are looking at, minus the step that the odd number started on. So let's look at this here. We have a 1, and that is the first term here. And then we multiply that by 2. But this 2 is raised to the power of n. N is just n. Let me move my mouse so you can see. N is just simply n. That's going to be the variable for whatever we're actually testing because of this formula. And then the 1 started on step 0, so we go minus 0. So we have 1 times 2 to the power of n minus 0. Now this is the same thing that I had over here. And if we look at that carefully, n minus 0 is just, well, n. And 1 times anything is just that thing. So we can kind of get rid of the extra stuff. And we have 2 to the power of n. And that's what this is. If we want to find out what this next value will be, we know that we're on step 16. We want to know what comes after this value on 17. We go, all right, 2 to the power of 17. And that will get us to, well, whatever this is times 2. This is, in fact, 2 to the power of 16. This is, in fact, 2 to the power of 15. This is, in fact, 2 to the power of 5. This is 2 to the power of 0. And this will apply to every single one of these. All these even numbers came from an odd number some point way back here. All of them. And all of these odd numbers will generate a whole new formula. So let's make a formula. Let's look at this. We have a 7 right here, and it is on step 16. So let's figure out what this is going to be. We have a 7. We have times, and let me move the mouse, 2 to the power of n minus step 16. close parentheses. So let's fill it in. Let's see what we're going to get after the 7 on step 17. We're not concerned about the odd number as far as this formula is concerned. We're just concerned about the next even number. And the reason why I'm showing you this, I guess I should have covered that. The reason why I'm showing you this is to show you that all even numbers will proceed into even numbers. All of them. And all even numbers come from an odd number. They all come from a root, and it's just a matter of doubling. And let's say the 280 right here, you're not going to get a 280 from anything other than doubling a 140. And you're not going to get a 140 from anything other than doubling a 70. You're not going to get a 70 from anything but doubling a 35. And you're not going to get a 35 from anything except, well, what's 3 times 35? Let's see here, that'd be 70. Plus 35 is 105. Plus 1, and this is 3n plus 1. We're going towards the 1 now. So 3n plus 1 of 35 is 106. And you're not going to get a 35 from anything but a 106. There's no way a loop is going to happen in this. If you look at this and actually understand what's going on here, a loop cannot happen. It will not. No trivial loop will come out of any of this. You'll get some interesting answers, but they're all very, very predictable. But let's go back to this here. That was a slight divergence, but it's an important one. Step 17, we want to see what comes after 7 on step 17. Well, we can do that in our heads. We can say 17 times 2 is going to become a 14. All right. Well, does this agree with us? 7 times, and then we have 2 to the power of 17 minus 16, because we're testing for n, which is step 17 in this case. 17 minus 16 is 1. 2 to the power of 1 is just 2, so 7 times 2 is 14. So let's go to step 18. 7 times 2 to the power of 18 minus 16. So, alright, we have 18 minus 16 is 2. 2 to the power of 2 is 4. 7 times 4 is 28. And lo and behold, immediately after the 14 comes a 28. And you're not going to get a 28 from anywhere else. And you can do this for every single number ever. And you just have to go, all right, here's an odd, here's an odd, here's an odd, here's an odd. We can make new formula for these. And the rest of these, well, we just have to figure out which odd value they came from. And I can actually put each of these formula in place. I'm not going to do that right now. You can just see what all of this does. Now, let me just re-emphasize this. This will show you that you're never going to get some sort of trivial loop. Every single value produces a formulaic chain that will only continue to double and double and double and double and double. You cannot double any number to create a number that is outside of that chain. You cannot double a 10 to get a 60. 10 times 2 is 20, 20 times 2 is 40, and then 40 times 2 is 80. A 60 is never going to crop up. There's not going to be a magical loop anywhere in this. So this leads me to sort of a different way of asking the Collatz problem. It's not whether every number will reduce to 1 without becoming a trivial loop. The question is instead, are there any numbers that do not fall within the Collatz chain? Because all numbers that do fall in the Collatz chain will always and irrevocably reduce down to a 1 without having some infinite loop of triviality way out here, some magical 421 of numbers that uh, unfathomably somehow could do it. Maybe somehow a square root of negative 1 popped in and threw a wrench into the works. No, it's never going to happen. Never will. All right, so let's look at these in a different fashion. Let's actually take some of this apart. Instead of looking at these formula, let's look at the chains that come from this. And this is one of the last few steps here, so I'm going to be able to kind of simplify this, I hope. We have the one chain, and I've colored that in black, and that goes down to the bottom here. But I've also included the 5 chain as black, just so the graphical representation here makes a little sense. And then whenever there's a new chain, as up to and including this row or this column here, I just start a new number, or a new color. So here we have red for 3 and 21, and both of these are the equivalent values for both hemispheres, or whatever halves that we're going to end up with. And then the blues on this step will just continue on a chain, and you'll be able to split things into sections the same way. Then here we have greens, and those will continue on. Then we have yellows, and those will split and continue on. And everything just continues to split and continue on. You can see that on the next step, all that isn't colored in by an existing formula chain is a new odd number here, 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 and and here. All 4 of these will produce whole new chains. 35 becomes 70, becomes 140, becomes 280. I could add a new color there. Same with the 213, that becomes a 426, new color. Or the 227, or the 1365. All of these will produce a new chain starting at this point, and they will all follow the same formula. And then all that's left to be discovered is what the new formula is for the odd numbers that creep up on the next line. So what can we get from all of this? First off, the top half of any section is in a ratio range to the bottom half, and it's going to be treated the same all the way down. Now, I do want to point out that the top and bottom halves, or the top and bottom quarter, and the top and bottom lower quarters, so quadrant 1, quadrant 2, and then quadrant 3, and then quadrant 4, I guess I could say. For each of the subdivisions, there are some instances where a single number pops in and does not have a reflection down in the bottom, or vice versa up in the top. So for instance, I wanted to take this example. This column here, this is step number 16. If I take the bottom half, which is this, and I take the top half, which is this, and I figure out the ratio, it ranges from 7 to 6.4. And there's a reason for that, and I'll show you in just a second. But as you can see, the range slowly trickles from 7 to 64. Now this is the big section. But if you take this small section here, and now that we are done with the lid, we can dispense with this 1536, or I guess we could dispense with both of these if you wanted to address either one of these, but I'm going to go with the one that's got an even number of items here. We have the 7 through 1664. I put that over here. Then we have the 46 through 10 to 40, or 10,240, and that put that there. And this ratio sequence still diminishes. It goes from 6.5 and some change to 6.15 and some change. Now, if you go farther out into the numbers sequence. Instead of stopping at 16, say stop at, I don't know, step 100. And you take just the top 12 terms, you're going to get an even slower drift from one term to another. As you get farther and farther and farther out, this takes a longer and longer time to get from the absolute top to the absolute bottom, and this increment just ever so slowly creeps, but it will always go from 7 to 6.4. And why is it 7 to 6.4? Well, that's because of something that happened way back here, and it keeps happening all the way throughout. This is what I call a split point, and the 16 becomes a 5 and a 32. Now the ratio of this is 6.4 to 1. 6.4 to 1, and you can see that more clearly here on this step. If you divide 64 by 10, you get 6.4 to 1. That's the ratio. But this ratio kind of squeezes together as the number line progresses, and that's because that is supposed to cover the whole chain. This number, which follows the 5, is going to always be in direct proportion to this number, which follows the 32, which is part of the 1 chain. So anything that happens on a row other than that is going to be ever so slightly different, and it's going to be slightly different to a ratio of 7 to 1. This is 1/7 of this, and it always will be, because this is 1/7 of this. Now, what does this mean? Haha, this is the glorious thing. This means that if we want to find the lowest value for any given sequence, it's always going to be in the upper portion because it is being divided first. This is always going to be a smaller bit. Yeah, you're going to get some arbitrarily close values every once in a while down here. So farther out, say the lowest value is a 111. That doesn't exist in this sequence. I don't see it anywhere. You might get a 112 down here, but that 112 is always going to be at least one greater than whatever the lowest value is. And that lowest value isn't just going to be in the top half, it's going to eventually start being in the top quarter, and then the top eighth, and so on and so forth, as you get farther and farther and farther out in the number of steps. The lowest value for each step is going to be this extraordinarily low number compared to everything else on that step, and it's going to be way at the top. Now, give me just a second here. I'm going to try to squeeze in some notepad. Alright, here we go. We have, for all the steps 0 through 49, and this is just where I stopped my program for spitting this out. On step 49, there are 62,680 numbers. That is an immense amount of things. You can see why I stopped at step number 16, because I didn't want to just keep expanding my graph and expanding my graph. Each one of these numbers is 26% bigger than the previous value. So we have the lowest value on step 149 is 100, or not step 149, step 49 is the lowest value is 169, and it is at the position 2,937 out of all that. That means it's way at the top. Yes, it's a lot further down than some of these others. Like here we have from step, let's see here, 39 to 43. Let me highlight these guys for you. All these happen at step 4, and there's some interesting patterns that you can extrapolate out of all of this additionally, but but these are kind of irrelevant. I don't know, maybe they might come into some equation later, but for right now they just show that the low value is going to be way in the upper portion of all this. And this is true. I've carried this on out to, let's see here, I want to say, I think about 980, 985 steps is where I finally decided to stop running it. Um, and then I noticed the trend, and then I started doing some additional calculations, and some of them are a little quirky. Actually, let me bring one of those up here. For just one of the different patterns that I started using to discover roughly where the lowest value is going to happen. And it's something that I call a pinch pair. You remember, if you watched the first video, the red wool on the graph showing that two consecutive numbers took the same number of steps to reach that value? Well, this is an artifact of two numbers following patterns coming from a split point. Here's an example of a split point, 16. And then here's an example of a pinch pair. And these two numbers are separated by 1. We have a 20, which comes from a 10, which comes from a 5, which comes from a 16. Then we have a 21, which comes from a 64, which comes from a 32, which comes from a 16. These are the two formula, let me go back over here, that are used to discover this. One of these is the 20 and the other one is the 21. And whichever one is divided into the smallest bit will always be farther north in this graphical representation of all the rest of the items. What this can do, though, is you can actually expand on this formula and find pinch pairs that aren't exactly graphically right next to each other. For instance, we have a 300 and a 301. Those are right next to each other. Cool beans. But that's 301 and 302. Well, those are also a pinch pair, but they just happen to be an artifact of a much more expanded version of that pair of equations that happened farther back. And what's happening here is the design of the Collatz conjecture, which all it does is produce whole numbers. If we were producing anything but whole numbers, none of this would be interesting. But since this is whole number production, we need to find multiplications and divisions that end up in a whole number answer. And if you follow certain paths, they will always generate a value that is one apart from another value the same distance from a given point farther back. That's what's happening there.